For this video, I'm going to continue to talk about equilibrium problems here, but we're going to more specifically focus on solubility equilibrium problems and the different types of problems related to that. We've already looked at this a little bit when we did solutions and we talked about KSP. KSP here is the solubility product constant. If you remember, KSP will tell you how soluble a solid is in water. Since solids do not change their concentration, they don't participate in the equilibrium expression. So if you remember, for these KSP problems, we have no denominator. All right. So if we look at an example here, and we've done this previously, one of these KSP problems, you have the solid substance, so in this case, calcium phosphate, dissociating into its ions. All right. Remember, this is the solid, and it's going to be in equilibrium with its ions that would form as it dissociates. So we have 3Ca2 plus, remember it's aqueous, plus 2PO4 3 minus, it's aqueous. You remember the amounts here of the things of each ion matters. All right, so we have 3Ca2 plus and 2PO4 3 minus. And since the equilibrium expressions do not include solids, we have no reactants in these. So we would write this as KSP equals the concentration of Ca2 plus cubed times the concentration of PO43 minus squared. Products over reactants, it's just that there are no reactants, and we still have to remember that the coefficients become the exponents for each of the substances here. We did KSP problems before, we just didn't use ice tables with them. So now we can actually do the same problems we did before, but this time we'll just use ice tables, and you'll see we get the exact same answers, pretty much going through the problems the exact same ways. So these next two examples we're going to do, we've seen, but we're going to do them with ice tables this time. Let's start with this first example. It says calculate the KSP for Mg3PO42 magnesium phosphate, given that its molar solubility is 3.57 times 10 to the minus 6 molar. Remember, there's only really two versions of these basic KSP problems. One version is when you are given the molar solubility and you're finding the KSP. The other version is where you are given the KSP and you're finding the molar solubility in each of the concentrations. So for this one, we are finding the KSP given the solubility. All right, so the first thing we need to do is write out our dissociation equation. So we have our Mg3PO42, our magnesium phosphate, which would be the solid, in equilibrium with each of its ions as it dissociates. So we'd have 3Mg2 plus, which would be aqueous, plus the 2PO4 3 minus, which would also be aqueous here. All right, so we just wrote out our solid dissociating into its ions, paying attention to the amount of each that forms. Now we're ready to do an ice table with this. Remember, this is an equilibrium problem, so we can do an ice table. It's just that for the solid here, solids don't participate in equilibrium. So there's nothing here written for the solid in that part of the ice table. That's something you just need to remember and be aware of here. So initially, our concentrations of Mg2 plus and PO43 minus are 0. All right, there's nothing present initially here. Our change for each of them, they are not present initially, so they're going to form. They're going to be positive for the change. And you do have to pay attention to the coefficient here. So we have plus 3x for the Mg2 plus and plus 2x for the PO4 3 minus. So now when we do our equilibrium concentrations here, we can actually plug in the value of x here. We know what the value of x is. We know the molar solubility here. If you remember, we said previously that if you know the concentration of this, you know that the concentration here of the Mg2 plus should be 3 times that value. And essentially what we're doing here using the ice tables, we're showing that the concentration of the Mg2 plus at equilibrium would be 3 times whatever x is. All right, if you know the molar solubility of this, you also know that the concentration of the PO4 3 minus would be 2 times that. And that's exactly what we're doing here. So when we have this version of the problem and they tell you the molar solubility, they're essentially telling you what x is. When they give you the molar solubility, that's the value of X. So the concentration of the Mg2 plus here at equilibrium is going to be 3 times the molar solubility. So 3 times 3.57 times 10 to the minus 6 molar. And then the concentration of the PO43 minus is going to be 2 times the molar solubility. So it's going to be 2 times the 3.57 times 10 to the minus 6 molar. All right, so that's very important to remember in these problems. The molar solubility is essentially X. And then when you get to the equilibrium part, you can plug that in for X. Now you need to write your KSP expression here. So it would be KSP is equal to, we have products over reactants. There's not going to be any reactants because it's a solid. So it's going to be the concentration of Mg2 plus cubed times the concentration of PO4 3 minus squared here. All right, so now we're just going to plug in what we know from the problem here. We're trying to solve for the KSP. So we know the concentration of the Mg2 plus is going to be 3 times 3.57 times 10 to the minus 6. And that's going to be cubed here. Remember, if you remember doing these problems without ice tables, we always said you had to multiply the concentration by 3, but then you still had to cube it because the cubing was part of the expression. And you can see here, same thing. The cube is part of the KSP expression, so that's why you need to cube whatever the concentration of the Mg2 plus is. And that concentration is 3 times the molar solubility, essentially. And then we're going to times that here by the 2 times 3.57 times 10 to the minus 6. And that's going to all be squared for the PO4 3 minus. So now this is just doing the math. I would make sure here that you can do this math and get the correct answer here. But your KSP with correct sig fig should come out to be 6.26 times 10 to the minus 26th here. All right, so that's a very low KSP, and it indicates here that this magnesium phosphate is not very soluble at all. So this is just a way of doing one of these KSP problems, solving for the KSP given the molar solubility. Just remember, in this version of the problem, the molar solubility is your X that you need, and it's going to be your concentration, essentially. It's going to be your X value, and then you have to plug that all into your KSP expression. For this problem, we want to calculate the solubility of CaF2 and the concentration of each ion given the KSP. So this is the other version of these simple KSP problems where you're given the KSP and you're finding the solubility and the concentration of each ion. Just like before in the other problem where the molar solubility was X, the same thing is going to apply here essentially. All right, the solubility of the compound, the molar solubility of the compound is going to be X for us. So first thing we got to do for this KSP problem, remember we did this without ice tables before, but we're going to need to do an ice table. We need to write our dissociation of the solid into its ions. So we have CaF2 would be our solid. It's going to be in equilibrium with its ions that form when it dissociates. So it's going to be Ca2 plus aqueous plus 2F minus, which is also aqueous. So now I'm going to do my ice table because it's an equilibrium problem. Remember, the solids do not participate in the equilibrium problem, so it's gone here from our table. Initially, there's no value. There's no Ca2 plus or F minus present. Therefore, we know that we're going to be forming products here, so the change is going to be positive for each of them. We do need to pay attention to the change in terms of X. Calcium is just going to be X because there's a 1 in front, but the F minus is going to be 2X because of the 2 in front of it. All right, so then at equilibrium, we don't know the value of X now. So our concentrations at equilibrium for each are just going to be X molar and 2X molar. All right, if you remember back to the previous problem we just did, they gave us the molar solubility in the problem. We knew the value of X right away. Here, we don't know the value of X. So now I have to write my KSP expression. So I got KSP is equal to products over reactants. There's not going to be any reactants this time again because it's a solid. That's what you'll see here for these KSP problems. So we have the concentration of Ca2 plus times the concentration of F minus squared. All right, so we're going to plug in what we know here. So this time we knew the KSP, so that's 4.9 times 10 to the minus 11, and that's going to be equal to the concentration of Ca2 plus, which we said was X, times the concentration here of the F minus squared. So F minus was 2X, but we have to square it. All right, so now you're just going to need to solve for X here. Again, I would make sure that you can do this math and solve for X. When you solve for X here, it does come out to be 2.3 times 10 to the minus fourth molar. All right, so now we want to know the solubility of the compound and the concentration of each ion. Remember here, X is the molar solubility of the compound. If you look at the ratio here in the balanced equation, for every one of this, there's one of the calcium. For every one of this, there's two of the F minus. So X here is the concentration of the Ca2 plus and the concentration of the CaF2. So when I write this out here, concentration of the CaF2 is equal to X, which is 2.3 times 10 to the minus fourth molar. Ca2 plus is the exact same thing. Remember, we want the molar solubility, the solubility of the CaF2, and the concentration of each ion. So the concentration of Ca2 plus is going to be 2.3 times 10 to the minus fourth molar as well. And then the concentration of the F minus has to be 2 times X. All right, don't miss that here. It's got to be 2 times X. So the concentration of the F minus is going to be 4.6 times 10 to the minus fourth molar. All right, so now I have the solubility of the compound itself and the concentration of each ion. Remember, we did these problems previously with no ice tables, but they can also be done and should be done now with the ice tables, and you do get the same answers here. All right, so just be able to do these basic versions of these KSP problems, either solving for KSP or solving for the solubility and the concentration of each ion. So in this problem, it's telling us the KSP value for CuIO32, and they want us to find the solubility at this particular temperature. So the first thing we got to do is actually write our equilibrium reaction here. So we know that the solid compound here, the CuIO32, all right, will be in equilibrium with each of its ions. So you have Cu2 plus, which would be aqueous, and 2IO3 minus, which would also be aqueous here. All right, so that's the reaction we're essentially looking at. The solid compound is dissociating into its ions in water. So we can set up our ice table for this particular reaction. All right, just remember here that for the solid compound, it does not participate in the equilibrium ice table. Remember, solids do not participate in our equilibrium constant. So we only need to worry about the aqueous products here. So initially, we know that each of these are not present. So they're both 0 initially. Since they're not present initially, they're going to be forming. So the Cu2 plus change would be plus X, and the IO3 minus would be changing by 2X here because of the stoichiometry with the 2IO3 minus. So then we can apply these values now at equilibrium. 0 plus X is just X molar, and at equilibrium the IO3 minus would be 2X molar. So now we have our ice table filled in, and we can go about solving this. The first thing we want to do, though, is we want to make sure we write our equilibrium constant expression here. And since this is a KSP, we know it's going to be KSP is equal to the concentration of Cu2 plus times the concentration of IO3 minus here, but squared. That's your products. And then we don't put anything on the bottom here because our reactant is a solid. So that is our equilibrium constant expression here. So we can plug in what we know. We know that the KSP, according to the problem, is 1.4 times 10 to the minus 7. And this would be equal to the concentration of Cu2 plus, which according to our ice table is X, times the concentration of the IO3 minus, which we know is 2x, but we have to square it because of the equilibrium constant expression. So when we actually start combining these things here, we get 1.4 times 10 to the minus 7th equals 4x cubed. You can divide both sides by 4, and we get 3.5 times 10 to the minus 8th equal to x cubed. Take the cube root of both sides, and we get x being equal to 3.3 times 10 to the minus 3rd molar here. And because the molar solubility is x in these problems, I know the solubility of the original compound. So this value here would be the concentration of my CuIO3 2. All right, this is my molar solubility. This would also be the concentration of my Cu2 plus, because that's X, but 2 times this value would be the concentration of my IO3 minus. So that's how you go about solving a problem using ice tables and equilibrium concepts for a molar solubility type problem. What does KSP actually tell us? If we look at KSP, basically it's telling us that everything is at least very, very, very slightly soluble. All right, nothing is completely insoluble in theory. So when we have substances that are insoluble, that basically means they are not going to go to the product side. Basically, that means they have a very, very low KSP value. But in theory, they're at least slightly soluble. Some products will form. It's just, is it even an amount that's actually detectable? So we can look at KSP to figure out which compounds are actually more soluble here. If you have KSP values for salts that produce the same number of ions when they're dissolved, you can actually compare the KSP values to figure out which is more or less soluble. If you have a different number of ions forming for the substances, then technically you'd have to actually calculate this using the KSP expression. But basically, if the substances have the same I value, if you remember I value here, the Van Hoff factor, you can actually just look at KSP values and figure out which substance is more or less soluble. We know here that a smaller KSP value will be or will make a substance less soluble. And this makes sense. Think about it in terms of products over reactants. Remember, your reactants in these KSP problems are always going to be the solid. So if you have a very small K value, that means you have a lot more reactants present. More reactants means more of the solid, meaning you are less soluble. So lower the KSP, the less soluble it's going to be. All right. If you have a higher KSP, that means you're going to form more of the products. The solid's going to dissociate into the ions. That's the same thing as dissolving. So a smaller KSP means it's going to be less soluble. Just think about this in terms of the KSP and the equilibrium constant expression, and it really does make sense. So if we're looking at these three compounds here, AGBr, AGI, and AgCl, they would all three dissociate into 2 ions. All right, so they all have an I value here of 2. So that means they all have the same number of ions when they're going to dissociate or dissolve. So we can actually compare KSP values to figure out which substance is more or less soluble here. So if you look at the actual KSP values for each of these substances, we should be able to figure out which substance is the least soluble. So smaller the KSP, the less soluble. So the KSP value here that is the lowest is the AGI, 1.5 times 10 to the minus 16th. So this would be the least soluble of the three substances. And then the one with the highest KSP would be the most soluble. So comparing what's left, the AgCl has the higher value. So this substance would be the most soluble here of the three substances. Okay, so if the substances have the same number of ions when they're dissolved, you can just look at the KSP values and make a comparison and see which is more or less soluble. Just remember, The lower the KSP, the less soluble. Lower, less soluble. There's going to be more of those reactants or more of the solid essentially, so less of it would dissolve. That's a big idea that you need to know. So the next type of problem we're going to see here is what I call a will it precipitate problem. These are problems where you will need to compare Q to KSP to figure out if a particular substance will precipitate or not. Just remember here, for these types of solubility problems, the general reaction that we're looking at is we have some form of solid in equilibrium with its aqueous ions here, essentially acting as our products. So the solid is like the reactant, and the aqueous ions, or the dissolving, is actually our products. So if you compare Q to KSP and it's less than, if Q is less than KSP, if you remember the alligator from class, that means the reaction is going to favor the product side, or you're going to need to form more products to reach equilibrium. So if Q is less than KSP, that basically means you're unsaturated because the equilibrium is going to go or form more of your aqueous substances, or it's going to dissolve more of your solid and form more of those products. So you're unsaturated. More of the solid can dissolve. If Q is equal to KSP, well, then you're at equilibrium. And then if Q is greater than KSP, if you follow the alligator, that means you're going to need to go to the left side or form more of your reactant, in this case, the solid, which that basically would mean you're precipitating out. So if Q is greater than KSP, that's when a precipitate will form, because the equilibrium will essentially shift to the solid side, or more solid will come out. So that's what we're looking for here when we do these types of problems. We need Q to be greater than KSP in order for a precipitate to form. So here's just an overview of the steps you will see in a will it precipitate problem. And I'm going to show you how to actually do one of these problems. So the first thing you do is you figure out which ions will actually form the precipitate. And then you need to figure out the number of moles of each of the ions in the precipitate. But you really do need to pay attention to the overall number of the ion in the compound that you're given. So that's something we got to watch for when we're doing these problems. Once you have the number of moles of each of the ions, you need to put the moles over the total volume of your new solution after you mix these things. And that will give you a concentration of each ion, which you can then plug that concentration into the Q expression here, and then you can compare what you get for Q to the KSP they gave you in the problem. So we're going to do all of these steps in a will it precipitate problem. And remember, if Q is greater than KSP, then a precipitate will form. All right, so if we look at a will it precipitate practice problem here, in this example, you can see it's asking, will a specific substance precipitate given that you're preparing it from a certain number of milliliters of a concentration of CeNO3 added to a specific amount of an MgIO3 and they want to know here, will this substance precipitate or not? So we're going to have to follow the steps. So the first thing is, if you look at the steps, was we have to figure out which ions are actually in the precipitate. Well, I can see here the substance they're asking me about. So I know that the CeIO3 is the substance they're asking me about in terms of the precipitate. So the ions that are involved here are the Ce3 plus and the IO3 minus. So they're the only substances I care about in the actual substances that they gave me here. So the first thing I need to do once I know the substances involved in the precipitate is to find the moles here of each of those substances. So for the first substance, I know that I have 750 milliliters of it. I need to figure out the moles here, so I'm going to need to get rid of the milliliters. There's 1,000 milliliters for every liter. And now that I have liters, I can use my concentration. I know that there's 4.00 times 10 to the minus third moles here. And this is the number of moles of my CeNO3 according to the concentration. Okay, and that's the number of moles for every liter because it's a concentration. So my liters cancel, and now I'm in moles of the compound. But you remember, we need the moles of the ion in this particular compound. So I only care about the Ce3 plus. So for every 1 mole of the compound, essentially how many moles or how many Ce3 plus are there in the compound? Well, there's only 1 moles of the Ce3 plus. There's only 1 Ce3 plus in the compound. So my units cancel here, and now I'm in moles of the Ce3 plus. So when I calculate this, I get 0.00300 moles of the Ce3 plus. Well, now I need to do the same thing here, but now for the other substance that I care about, the other ion I care about is the IO3 minus. So I know that there's 300 milliliters of that substance. Again, there's 1,000 milliliters for every liter. This will allow me to get to liters so I can use my concentration. And they're telling me there's 2.00 times 10 to the minus 2 moles, but this is the number of moles of the MgIO3 2. And there's that many moles for 1 liter because it's a concentration. So my liters cancel. I'm now in moles of the compound, but again, I need moles of the IO3 minus ion because that's what's involved in my precipitate. So I know now that for every 1 mole of the compound, the MgIO3 2 here, there are 2 moles, according to the formula, of the IO3 minus. Okay, so that's what we mean by pay attention to the number of the ions in the compound itself. All right, so there's 2 IO3 minus essentially for every one of the compound. So when I solve this for moles, I get 0.0120 moles of the IO3 minus here. All right, so I found the moles of each of the ions in the precipitate that I'm being asked about. So now what I have to do, if you look at the next step, is you have to find or divide this by the volume because we're trying to get to concentration of each of these ions. So if I look in the problem, okay, I mixed 750 milliliters with 300 milliliters. So that is a total of 1,050 milliliters for my new total volume of solution. So essentially, there's this many moles of Ce3 plus floating around in 1.05 liters of solution. Essentially, it's 1,050 milliliters. I just converted it to liters so that I can quickly find the concentration or moles over liters here. So you do need to be in liters because you want to find the concentration, but you got to total up the actual number of milliliters you're mixing. And then the IO3 minus is floating around in the same number of liters here. So now I can find the concentration of each of these. So the concentration of the Ce3 plus, when I solve for this, ends up being 0.00286 molar. And then the concentration of the IO3 minus ends up being equal to 0.0114 molar. So now I have the concentration of each of the ions in the precipitate that I care about. I can move on to the next steps of this type of problem. So now that I have the concentration of each of the ions in my precipitate, I need to plug that into the Q expression. So before I do that, I want to write out the actual reaction here for my dissolving of the compound itself. So I have this CeIO3, which would be a solid, in equilibrium with each of its ions, the Ce3 plus, all right, which would be aqueous, plus the 3IO3 minus here, and that's aqueous as well. So I can write the Q expression from this as being Q would be equal to here the concentration, remember products over reactants, so the Ce3 plus times the concentration of IO3 minus cubed according to the Stoic. And now what I can do is the concentration of these ions that I found previously, I can plug into my Q expression here. So when I do that, we plug in those concentrations. So we have the Ce3 plus was 0.00286, and the IO3 minus is 0.0114, but that is cubed. And when I solve this, I get 4 times 10 to the minus ninth as my value of Q. So when I compare these now, I have 4 times 10 to the minus ninth for my Q, and I have, according to the problem, 1.9 times 10 to the minus 10th for my KSP. So when you compare these numbers, the Q, because it's minus ninth, is actually greater than the KSP, which is minus 10th. So according to this, if you follow the alligator, the reaction is going to shift to the left side, or more of the solid is going to form. Therefore, yes, a precipitate will form. Okay, so I know all you're really answering is yes, a precipitate will form, but you do have to show all your work to prove this. So you need to find the number of moles of each of the ions in the precipitate, find the total volume of the solution, and then you find the concentration of each of the ions, and then you can plug that into your Q and compare Q to KSP. If Q is greater than KSP, then a precipitate will form. Let's look at another practice problem here. Um, Maybe it's a good idea for you to pause the video and try this one on your own to see if you can do this, and then rejoin the video and I'll have the problem completely solved for you so you can see how you did. You definitely need to be able to do these problems on your own. So I would pause the video right now and try this problem on your own. So hopefully this is the answer that you got here. Make sure you're checking your work because just saying yes is not enough. You actually have to get this value of Q and compare it to the K. And you do get points here for your work and getting the correct answers. So the first thing you need to do for this problem is realize the precipitate that we care about is the FeOH3. So the ions that are most important to us are the Fe3 plus and the OH minus. So what we need to do here is determine the number of moles of each of these ions in the various solutions here first. So I knew in the 500 milliliters of the FeNO33, the only ion I care about is the Fe3 plus. So you take the milliliters that you started with of that, get it to liters, use the concentration of that solution, which gives you the number of moles essentially of the FeNO33, but we only care about the Fe3 plus in that. So for every one of the entire compound, there's just 1 mole of Fe3 plus. That gets us to the moles of Fe3 plus, which is what we care about. You do the same thing for the other solution here, the NaOH, but this time we only care about the OH minus in there. So once you get to liters, you can use your concentration of the NaOH, but remember, that's the number of moles of NaOH. We only care about the moles of OH minus. So for every 1 mole of NaOH, there's just 1 mole of OH minus in that compound. So now that we're in moles of OH minus, now we need to get each of these moles to concentration. So if you add up your total number of milliliters here, 500 milliliters, 250 milliliters, that gives you 750 milliliters. Put it in liters. So you divide essentially each of the moles by the number of liters here. That'll get you the concentration of each of the ions that we care about. Now that we have the concentration of each of the ions in the precipitate, we can plug those concentrations into Q after we write our KSP expression. So write the KSP expression here for the dissolving of this compound. Don't forget that the OH minus would be cubed here according to the expression. Plug in these concentrations into the Q expression, solve for Q. Compare Q to KSP. Because Q is greater than KSP, essentially what that means is the reaction would shift here. If you follow the alligator, the reaction would shift to the reactant side, which if you look up here, the reactant side is the solid. So that means essentially here, this will precipitate out. The solid is going to form as you shift to the reactant's side. So yes, this would precipitate. Again, you need to actually go through, do the work, and show the proof here, not just write that yes, it would precipitate. All right, so you definitely need to be able to do one of these will it precipitate problems. The next type of problem we see here are problems involving a common ion or the common ion effect. The basic gist of this is that there is always a reduction or a lowering of the solubility of a precipitate whenever you add or mix in a compound that has a similar ion in it. So basically, you are adding a substance that has an ion in common with the precipitate you're looking at. And that will therefore lower the solubility of your substance. So it won't be as soluble because of that common ion that's there. So anytime you see a similar ion being added to your precipitate here, you are always going to have a reduction in the solubility. So we ignore the ion that's not common and focus on the common one. So if you can see in the little example here, it says if you add 0.10 molar NaCl to a solution of AgCl, the Na plus ions in the NaCl have no effect here because they're not in the AgCl. But now essentially you're adding more Cl minus ions. So this affects the solubility. So the AgCl, because of the presence of more Cl minus ions, is not going to be as soluble. So it's actually going to precipitate out some more. So less of the AgCl will be dissolved. That's a common ion effect. The substance here, the AgCl in this case, is less soluble than it was because of the presence of another Cl minus ion or more Cl minus ion. That's the common ion effect. Let's look at this example. It says we have a 0.1 mole sample of solid AgNO3 added to a 1 liter saturated solution of silver chromate. Assuming there's no volume change, does the concentration of the CrO42- increase, decrease, or remain the same? And justify your answer. You don't need any calculations here. All right, so it looks like we are adding silver nitrate here to this. So the part of the silver nitrate that we care about is the silver, because that's what's in common here with our solution, essentially. The silver is in the silver chromate. So according to the common ion effect here, there's going to be a reduction in the precipitate when you add here a substance that has one of the same ions, all right? So there's going to be a reduction in the solubility. All right, so it's going to be less soluble here. All right, so what that means is if we add this silver nitrate here to the silver chromate, the substance is going to be less soluble. So that means less of the ions will form and it will stay in the solid form more. So does the concentration of the CrO42- increase, decrease, or remain the same? It's going to decrease here because of the common ion present. Essentially, this will reduce the solubility of the silver chromate, which means it's not going to form ions as much. It's going to stay in the solid form. That's what a reduction in solubility means. It's not as soluble. All right, so you won't see the ions forming, and more specifically, you won't see this CrO42- forming as much because you have less solubility here. So that concentration would decrease. And that's how you can explain this without needing a calculation. So let's look at an example of a common ion effect problem here. So in this case, this wants us to find the equilibrium concentration of the Mg2 plus in a solution of MgF2, and they gave me the KSP for it, but they're telling us we have 0.100 moles of solid KF being added. We're assuming that the KF dissolves completely and that any volume change associated with the addition of a solid here is negligible. Okay, so our volume is essentially staying the same. So you can see here that this is not like exactly like a molar solubility problem because they're telling us they added something to this. All right, but it's going to be very close to one of those molar solubility problems that we saw earlier. Okay, so the first thing we need to do here is realize, hey, look, we need concentrations. All right, they're telling us that we're adding 0.100 moles of the solid, but our overall volume is 1 liter. So essentially, we know that we have 0.100 moles in 1 liter. So our concentration when we add the KF is going to be 0.100 molar. So it's very important. Just be careful with how these problems are worded. If they give you moles, pay attention to the number of liters you're dealing with. You do need a concentration here. All right, so now that I have my concentration, I need to actually write out my equilibrium solubility here. So essentially, I have my MgF2 here, which is my solid, and that is in equilibrium, all right, with its ions, the Mg2 plus, which would be aqueous, and 2F minus, which is also aqueous. All right, so that's the actual reaction I'm looking at. I can set up my ice table. Okay. Remember, the solids do not participate in the ice table. They don't participate in the equilibrium here. So initially, I don't have any of the Mg2 plus, but then here's the difference. Okay. In a common ion problem, one of your initials is not 0. This is different from the molar solubility problems we did, where both were starting at 0. So in this case, we added Kf. F minus is the common ion. So instead of having an initial value of 0, we actually have an initial value of F minus as being 0.100 molar from the common ion. So that's the big difference in a common ion problem. Both of your ions are not 0. One of them is going to have a starting value, and it's going to be based on the common ion of the substance that's being added. So in this case, Kf was added, and F minus is the common ion, and we know the concentration of that. We already found it. So that is the initial value of our F minus. And then everything else here is pretty much the same. If we look at our change in concentration, we know we're going to be forming products here. So this is going to be adding some value of X. This one's going to be adding some value of 2X. So at equilibrium, this would be X molar, and this would be 0.100 plus 2X molar. Okay, so don't forget here that we had a starting value for this one, so it's not just 2X. So now I can write my KSP expression here for this. I know KSP would be equal to the concentration of my Mg2 plus times the concentration of my F minus squared here. All right, so now when I plug in the values here, I know I had a KSP of 7.09 times 10 to the minus 9th, and that would be equal to X for my concentration of Mg2 plus, and then my concentration of F minus is 0.100 plus 2X, and this would be squared. Now, because the KSP here is times 10 to the negative 9th, we can assume that any change here would be negligible, so we can always usually eliminate the plus X amount here from one of those ions. So that's good. It makes our math here a little bit easier. So when I solve this for X, and you can go through and do the math, but when I solve this for X now, remember, don't forget to square your 0.100. When you actually solve this, you should get 7.09 times 10 to the minus 7th molar. All right, and because they're asking for the concentration of the Mg2 plus, according to my ice table, the concentration of the Mg2 plus is X. So now that I found X, I know that that is the concentration of my Mg2 plus. So that's how you go about solving one of these common ion type problems. Very similar to the molar solubility problems, with the exception of you're going to have a starting value for, or an initial value for one of your aqueous substances, and you can eliminate, usually because the KSP is very low, you can eliminate your X in your calculation for the addition here. So that is a common ion type problem. So the last type of problem we're going to look at here is a which precipitates first problem. Basically, you will be trying to figure out which substance will precipitate out first whenever you're adding a particular substance to it. So these have a specific set of steps as well. The first thing you do is you write the KSP expressions for both possible precipitates. You substitute in all known values, and then you solve for the concentration of the ion that's being added here. Essentially, that's your unknown. And the idea here is that when you say which one will precipitate first, when you calculate these concentrations, you will obviously reach a lower concentration as you're adding a substance before you would reach the higher concentration. So the one with the lower concentration will precipitate out first. Typically here, we're going to have to do calculations, but if no calculations were required and the substances form the same number of ions when they dissolve, you can just look at the KSP, and the one that has the lower KSP will precipitate first. But like I said, typically we're going to have to show our work and show the process here. So we don't see that too often. All right, so in this example, they're telling us that a solution contains a certain amount of Cu plus ion and Pb2 plus ion. And they're saying we're adding some source of I minus gradually to this solution, and they want to know, will Pbi2 or Cui precipitate out first? And they also want us to give the concentration of the I minus that will be necessary to make these substances precipitate. Okay, so according to the steps, the first thing we do is we write the KSP expression for each of the possible precipitates. So first, I know I have my PbI2 here, right? That would be my solid, and it would be in equilibrium with its ions, which would be Pb2 plus and 2I minus here. And my other possible precipitate is the Cui here, and that would be in equilibrium when it dissolves with its ions, the Cu plus and the I minus. All right, so when I write the KSP for the PbI2, the KSP would be equal to the concentration of the Pb2 plus times the concentration of the I minus squared, and the KSP for my Cui would be equal to the concentration of my Cu plus times the concentration of the I minus. All right, so I wrote the KSP expression for both of my possible precipitates, and now what I do is I plug in what I know for each. So obviously I know the KSP value here. We'll start with the PbI2 side. This is 1.4 times 10 to the minus 8th. All right, they told me the concentration of the Pb2 plus. If they didn't give me the concentration of the Pb2 plus, I'd have to find that depending on how this problem was set up, but they gave it directly to me in this. So I know the concentration of the Pb2 plus is 0.0020, okay? But I don't know the concentration of the I minus because that is what we are adding here. Okay, we're adding the I minus to the solution. So I'm trying to figure out the concentration of the I minus that would make this precipitate out. So when I solve this for the concentration here of the I minus, so you do the math here, you should end up getting the concentration of the I minus to be equal to 2.6 times 10 to the minus third molar. Okay, so that is the concentration of I minus that would be needed here to precipitate out the PbI2. So if we look at the Cui now, I do the same thing, plug in what I know. They gave me the KSP to be 5.3 times 10 to the minus 12. And they told me the concentration of the Cu2 plus was 1.0 times 10 to the minus 4th. But again, I don't know the concentration of the I minus because that's what I'm solving for. So when I do my math here and solve for the concentration of the I minus, I get it to be 5.3 times 10 to the minus 8th molar. So let's just review here what we did so far. We wrote the KSP expression for both possible precipitates, plugged in the values we know, solved for the concentration of the unknown, or the one we're adding. So now what we do is we compare these two, all right? Obviously, if you were slowly adding I minus to this solution, okay, the concentration of the I minus would slowly start to increase, all right? So the lower concentration of these two would be reached first. So if I compare the two here, the CUI would actually precipitate first because its value of when the CUI will precipitate is when I minus has a concentration of 5.3 times 10 to the minus 8th, which is lower than the concentration of the I minus needing to be 2.6 times 10 to the minus third for the PBI2. So the CUI is going to precipitate first here because its concentration is lower for the I minus, and that concentration would be reached first, so it would precipitate out long before the PBI2 would, because the PBI2 needs to reach a concentration of I minus to be 2.6 times 10 to the minus third before it could do it. But then the follow-up question here is that it wants us to specify the concentration of I minus necessary to begin the precipitation of each salt. Well, we already did that, okay? This is the concentration of I minus needed to precipitate out the PBI2, and this is the concentration of I minus needed to precipitate out the CUI. All right, so that's how you do a which precipitates first problem. Write the KSP for each of your possible precipitates, plug in what you know, solve for the concentration of your unknown or the substance that's being added, and the lower value of your substance being added will be reached and therefore precipitate out first. So just a recap here of the different problem types that we could see. You could be asked to find the KSP, or molar solubility. That's where you use an ice table. Very important to figure out here which ones you actually use ice tables for. You use an ice table for this. You don't include your solids in the actual ice table calculations. And when you solve for X, X is the value of the molar solubility. You could see will it precipitate problems, and for those types of problems we do not use ice, so no ice table for the will it precipitate types problems. You simply find the number of moles of each of the ions in the precipitate, pay attention to the number of the ion in the actual compound you're dealing with. You figure out the concentration of each of those ions, and then you plug the concentration into your Q expression and compare that to KSP. If Q is greater than KSP, a precipitate will form. We also have common ion type problems here. Again, common ion problems, very similar to molar solubility problems. So you do use ice tables here. You are allowed to use the X approximation where we can cancel out our added value of X because usually these have a very low KSP. The only difference here really is that one of your ions in your ice table will have an initial value, okay? So you will have an initial value for one of the ions in your ice table initially, and that changed the problem a little bit, but otherwise it's pretty similar, and the solubility of the substance you're dealing with is always lower because of the addition of a common ion. And then the last type here is a which precipitates first problem. Again, this type has no ice tables involved, okay? You write the KSP for both possible precipitates, plug in your values, solve for your unknown concentration, and the unknown that has a lower concentration would be reached first and therefore precipitate out first. So those are generally the types of problems we will see involving equilibrium with solubility and KSP.